about feedback-free galaxies.
Hi, can you hear me? Okay, yeah, so hello everyone. So I wanted to talk about our ongoing work on getting some echo. Yeah, so I want to talk about our ongoing work on the growth of massive black holes and FFB galaxies at cosmic dawn. Okay, so we have heard throughout the conference about overmassive black holes being found by JWST, and I'm just showing here observations. It's a compilation by Fabio from various studies, and so what we see is that we find in the local universe, if you look at the stellar mass, like the black hole stellar mass ratio in local universe, it's much lower than what we are finding at high redshifts. So at high redshifts, we're finding something of the order of 1% or even larger. And we want to sort of see if we can explain that within the scenario of feedback-free starbursts. And we heard from Zhao about the model. So basically at high redshifts, around redshifts of 10, if we have halo masses of about 10 to 11 or higher, then the densities are such that the star formation is very efficient. So we can form stars essentially in a feedback-free way. So if our densities are above a certain threshold, then the free-fall times are very short, and if we can form all our stars before the first stars go supernova, so we form stars in a burst, and also we need to avoid the radiation pressure, so that's why we have this condition. So this is where the gravity dominates over radiation pressure, so we can have effective collapse, and so we can form stars in clusters. So we form stars in around hundreds or thousands of clusters. And so how does this tie with black holes? So once we have this FFB clusters, then what can happen is that core collapse can happen within these clusters. And again, we need to do core collapse very quickly. We need to do it before the first stars go supernova. And the way to do that is if you have, so one way that helps is if you have young massive stars. So in that case, by mass segregation, the more massive stars will tend to migrate inwards, and that will help in core collapse. And the other thing that we found is that if the clusters are rotating, so if you have rotation, then there's an additional instability in addition to the standard gravothermal instability, which is called gravogyro instability. So basically, if you have a core which is rotating, and then there is an envelope which is rotating slower, so if differential rotation, then there's transfer of angular momentum from the core to outwards, and as a result of that, the core speeds up, so that the angular momentum transferred outwards, the momentum inertia decreases, the core speeds up, and so it's a runaway process, and so that helps in sort of making core collapse happen fast. And so it can lead to the formation of very massive star, and what sort of previous simulations have shown is that you can form a very massive star of the order of 1% of the cluster mass. But these simulations sort of were done with so the results that we quote here are from these simulations, which were done with a standard IMF. So we actually haven't simulated both the effects together, so that's another interesting thing to look at. But for the moment, I will assume that this works, and we can do core collapse very quickly, and we can form seed black holes, which are 1% of the cluster mass, within sort of 3 million years. So then, starting from these seed black holes, what will happen is that these clusters will start interacting. So we have these clusters, we have these black holes, and then the clusters start interacting with each other. The clusters can strip one another, and the black holes can sort of start to migrate towards the center by dynamical friction and sort of form a more massive black hole at the center. So we did a feasibility study, which was led by Avishai in his 2024 paper. And so basically, we arranged the clusters in a disk. And again, we need a rotating disk because we want the clusters to be rotating for core collapse to happen faster. And we also need it for faster dynamical friction. Because in a disk, the dynamical friction is more efficient than it is in a spherical halo. And we basically found that in this simple analytical study, we could sort of form 10 to the 7 solar mass black holes pretty quickly by redshifts of 7, basically aligning with the JWST observations. And now we have started to look into this using simulations. So I'm going to show you first results from simulations where we put equal mass clusters. So all the clusters are the same mass, and so we put 10 to the 7 solar mass clusters. Each has a size of 7 parsecs, so the effective radius is 7 parsecs. And we have a total mass in the disk, which is 1.5 times 10 to the 9 solar masses, so basically that gives us 150 clusters. And there's a density profile. I'm not going to details, but basically we have a cluster. There's a black hole at the center of each cluster, and so we need to make it somewhat steep in order to get an equilibrium distribution, so the plumber with a central steepening. And then we have a disk which is exponential. The scale, so it's an aspect ratio of about 1/10, so the scale height is 1/10 of the scale radius. And we also have a live halo. And so this is how the initial condition looks like. This is the live halo. This is the exponential disk of clusters. And this is just looking at the dispersion profile. So it's a rotating disk. So this is the rotation velocity in the azimuthal direction. So Vz and VR, they're 0. And then we have a dispersion, which is at least, so V over sigma is at least 1 to start with. So in the central region, and it increases. So we are dominated by rotation. In the outskirts is about 10 or 20. And so we run these simulations using Ramses. So we have a particle resolution of about 300 solar masses, the box size of 14 kiloparsecs, and we have a base resolution of 27 parsecs, and we can go to maximum resolution, so up to 0.4 parsecs. And we have checked that this is a good enough resolution. So we simulated the clusters in isolation, and we are confident that the clusters do not artificially disrupt. So this is a good enough resolution. And the way black hole mergers work is that if two black holes will come within a certain distance and we fix it to be 2 times the maximum resolution, so then they will be bound. So and if they're bound, so if two black holes come within this distance and they're bound, then Ramses will actually merge them. So we are not resolving the final parsec, so we don't resolve what happens inside this. We basically merge them when it comes within this and they are bound. And then there are, so when mergers happen, the spin of the black hole will be updated, and we have spin-dependent gravitational wave kicks. Right? So we have fitting formula, two GR simulations, and so the subgrid module for gravitational wave kicks. And this was implemented in this paper by Dongpei et al. In 2025. So now let me show you the results of this simulation. So we have all these equal mass clusters. So what you see here is the face-on view. This is the edge-on view. And so initially it's all red. So it's color-coded by spin. So initially it's all red. And then as black holes will merge, you will see different colors appearing. And so mergers can actually happen all around the disk. So when we have these, so it's a disk, right? So the interactions are very strong, and so two clusters can merge even out from the center, far out, and that will lead to black hole mergers. And then they can start to sort of strip, and at some point we'll have like these black holes without the cluster surrounding them. And then the clusters can also migrate inwards by dynamical friction from dark matter, since we have a live dark matter halo. But what is interesting to sort of see is, I don't know if you looked at this, but so as this simulation goes, you see these black holes sort of flying out. So these are the ones that fly out by recoil. And you see many, many black holes sort of flying out. And so basically if we think about what's happening, so we start from two black holes, or we have all black holes with equal mass. And so when two of them will merge, initially we have a mass ratio of 1. So if mass ratio is 1, then there is no recoil. Right? But as soon as two of them merge, then we are here. So basically we are at 0.5. For the third merger, which will happen with another black hole, we are at 0.5, and the recoil is very strong. And we'll also have some spin orbit misalignment. There's always going to be some spin orbit misalignment. And basically you can have very strong recoils. And So if we look at this plot in the mass radius plane, so this is the mass of the black hole and this is the radius of the black hole. So this is the initial condition. We had all the black holes with same mass and an exponential distribution. What happens with time is that central black hole is not growing. So most of the black holes are getting kicked out, and if you look at how much mass got kicked out, so about 63% of the total mass in black holes that got kicked out, and so we basically sort of decided to stop the simulation here and not run it any further. But you can also do a control simulation where we artificially switch off recoil, and if we switch off recoil, then we can grow. So we can grow a 10 to the 7 solar mass black hole pretty quickly. In about 100 million years, we can grow it into a 7 solar mass black hole. So what do we do next? So then basically what seems to be happening is that with equal mass black holes, we cannot grow them because the recoil is too strong. So then we thought, okay, let's play with the mass function. Let's play with the mass function for the black holes. And so here what we have done is that we have put in a mass function for the black holes. So now our black holes go, so basically it's a mass function for the clusters. So the clusters go from 3 times 10 to the 6 to 10 to the 8. Now I was wondering whether this is crazy, whether you can have so massive clusters, but like yesterday, Lucio showed us his simulations where I think he had a distribution of clusters going up to sort of 10 to the 8 solar masses. So maybe it is not that crazy. And so then we put black holes in each of these clusters, and again assuming that the black holes are always 1% of the cluster mass, and the clusters are distributed with a power law mass function. And we just, for this particular simulation, we just assume the power law slope of 1.4. So now let's see what happens. We run this simulation once again. Now we have all these clusters with different masses, and now you'll see that only one black hole. So that's the one that flew out, and we have run this for about 200 million years now, and we do see a central black hole growing in this case. So we can look at it a bit more. So you see all these clusters sort of moving in, the black holes moving together with them, and you start forming a central black hole. So if we look at the same mass radius plot again, so we have all the black holes with mass function now, and so it is growing, so we can grow a central black hole, but you also have other massive black holes, other off-centered massive black holes that are growing, and that's just because of the recoil. So you not only grow the central black hole, but you also kick some of them out. So one of them has escaped, which is this. So this has basically escaped the halo, but then there are others which are on eccentric orbits, and eventually they'll probably decay. We just need to run the simulation further, and this is another case where there is no recoil, so control with no recoil, and you basically grow it into a 7 solar mass black hole again very quickly. So we need to see what happens further, whether we can grow this further or not. Just showing the mass tracks so this is the central black hole that is growing, this is the evolution in the mass, and you see the radius, so it started from here, it's growing in mass, and it's gradually decaying. So it got 2 very strong kicks, one was here, another was here, but it sort of managed to stay, and I'll sort of try to say why. And then this is the one that escaped. Sorry. Yeah. So this is one of them which is decaying and will pretty soon very quickly merge with the central one. This is the one which is a bit tricky. This got kicked. It's on a highly eccentric orbit. Seems like it's decaying, but it may take a long while to sort of decay to the center. Now, how are we able to avoid those 2 strong recoils that we got? So I think what's happening is that as these clusters move in towards the center, it's deepening the potential. So all these clusters move in by dynamical friction, the black holes move along with them, and basically, so in the dark matter, we form a slight core. We tend to sort of form a slight core in the dark matter, but what is more important is that we are bringing a lot of baryons to the center, and we are deepening the potential. And so if you look at the escape velocity, we started with something around 600 kilometers per second, but we have increased the escape velocities to something like 900 kilometers per second. So this is not compaction driven by gas, but it's compaction driven by the motion of these clusters, which is boosting the escape velocity in the central region. So let me summarize. So feedback-free starbursts in massive galaxy at cosmic dawn, it's a highly efficient star formation process, and we form stars in order 100,000 clusters, few parsecs in size. Core collapse within these clusters, if it happens sufficiently quickly, can give seed masses of about 1% of the cluster mass. And in absence of recoil, these seeds will migrate very quickly to the center, as I have shown. In absence of recoil, you can basically get 10 to the power 7 solar mass black holes in about 100 million years. In presence of recoil, it's a bit less efficient, so now we form multiple massive black holes, both central and off-centered. So we can grow up to a few times 10 to the 6 in 200 million years right now. But we do need to sort of see what happens with different, because I just picked a particular slope, and I have a particular minimum mass, maximum mass. So we do need to sort of play with the slope of the mass function, the maximum mass, and also there's going to be quite a bit of realization variance because it's discrete, so it's only 80 or 100, 150 clusters. So it's going to be variance from one realization to another, even if we just sample a different realization. And so far, we have ignored gas in our work. So gas drag and gas inflow-driven compaction, which can further sort of boost the escape velocities, further deepen the potential, that can also help the growth of the black hole. And finally, of course, if you can grow it to a few times 10 to the 6 by this method, by this merger-driven scenario, then at some point, like there is going to be later accretion of gas onto the halo, and so the black hole can also further grow by gas accretion. So I'll end here and take questions. Thank you.
All right. Look, do you want to set up? And I think in the interest of time, maybe we can hold our questions for lunch or the discussion section, just because we're at the nominal end of the session. Let's thank Dhruba one more time. Thank you.